Okay, thanks, Stella, for agreeing to give a talk at this workshop. Stella is a professor at University of Michigan, Ann Arbor, an adjunct professor at University of California, Berkeley, and the director at the ICSI Vision Group. Her research lies at the intersection of computer vision, human vision, and machine learning, and she will be presenting a talk titled Learning Mid-Level Vision from Nothing But Data. I'll let you take over, Stella.
Okay, great. Thank you so much for having me. And I will start with learning from nothing but data. So what can we learn when we only have data? When we look at these videos, you probably see a mother carrying a baby, a car moving around. Everything is clear to you. But we have to realize baby vision is very different from grown vision. Grown vision has very sharp focus, and every scene you tend to see what's in the foreground, what's in the background. You're not distracted by the slight shaking of the camera or other irrelevant light fluctuation. So what would, babies have big eyes, but these eyes are what to see and how to see is yet to be developed. A proxy of what babies think, I will use this video to illustrate. A lot of light is flickering, and what should the baby be focusing on? And this, I liken this problem to, I try to visualize this in my mental imagery. I liken this to figuring out from a boiling hot soup. Everything is hodgepodge. And this is what William James, the father of psychology, named blooming, buzzing confusion. So many possibilities, yet so much confusion. And the baby needs to figure out this soup, there are isolated ingredients in them. How can we go from this undivided sensation to this bounded rationality? How do we make sense of the visual data? The first work I want to describe is our unsupervised learning of generic objectness. Given unlabeled video collection, we want to learn the model how to see. The goal is that given an image, we want to be able to put a hotspot on each frame of the video so that this hotspot indicates the potential object of interest, which correspond to some visual concepts that persist in the visual world. When we formulate this in computer vision, there's a very clear formulation we can come up with. Given all the videos, each frame, we want to pick out objects that are moving. We don't differentiate what they are. We cannot tell whether these are cats, dogs, person, so on and so forth. But we want to isolate these discrete events from the background that we are less interested in, or they don't have a continuous permanence. So what are the challenges? When we look at this image, this video, the task does not sound too challenging, because even based on color, we can pick out the brown elephants against the green grass. Now, if we look at this, if I pause the frame without the green box outlining the object, it's very hard to see there is an object moving at all. And only when the objects start moving, then figure ground becomes salient. So obviously motion plays a role, but in reality, we have, in majority of videos, we have these two sets of cues, both at work. One stream, you can segment the image based on the color and appearance. On the other extreme, that the motion cues is giving the figure ground segmentation. In the center, giraffes moving. The giraffe's body and the legs, they are of different spotty texture versus the wide legs, and the head is yet different. And every leg is moving, it's a different speed in the visual stimulation on our retina. yet we see the crowd moving with a constant speed. So how do we do that? And when you have motion, supposedly it gives additional cue, but it also introduces additional complexity. Here you have alligator moving in depth, and the appearance is very similar between the skin of the alligator and the water. And when you have motion, you can see that what you see in individual frame versus the whole video is quite different. And then you have this too much motion, too much flickering, and it's very hard to figure out which motion is actually relevant to the scene. Object segmentation from unlabeled videos can be considered an image sequence segmentation problem. This is our goal. Given a sequence of frames, we want to segment the foreground from each frame. In the past, there have been so many efforts on this, but the major line of thinking is that the sequence of images provide us the additional optical flow information. So we know how one frame moves to the next frame for each pixel. And then the segmentation problem becomes a cue integration problem. You have these appearance and motion cues. We, on the other hand, take a very different approach. We have the initial problem solving this unknown segmentation. We introduce another set of unknowns. These are also flow, but the flow is not per pixel. It is per pixel, but it's the segment flow. Every pixel in the same segment, we assume they move at the same speed. It's a great simplification of what's happening. Now, given a sequence image, we want to solve two sets of unknowns together. And that actually simplifies the problem. So what is flow? A quick briefer on the concept of flow, which is simply the displacement across frames in the 2D image. Consider this scene, and this horse moved in different location in the second frame. And so if we look at the traces of movement, each pixel will have a corresponding location in the 2D image plane. And that becomes a displacement vector for each pixel. In the traditional optical flow definition, we are solving the local displacement per pixel. You look at the patch at this location, you look around in the previous frame, and you find here I have a perfect match between the left and the right. And there I figure out the delta X. So this equation, try to minimize appearance differences. This set of equation I and J denotes the two images at two time instances. They are specific to the image pair, and it's solved independently between pixels. Our segment flow assumes constant displacement per segment. We still try to minimize appearance differences, but we are learning this statistical relationship. The loss is accumulated over all the training pairs of I and J, and we assume that the flow is the same per segment of a segmentation. It's all nice, seems clear. The trick is that the segmentation is unknown. We don't know how to do segmentation. So we propose to concurrently learn segmentation and flow estimation. Here's a schematic. We learn segmentation per image. Given frame IX, we can predict pixel-wise segmentation label. Segmentation, not label. Given two images, we can calculate the flow estimation. These are two networks to be learned. And if we know how each pixel moves from the flow estimation, if we know that how the scene is made of these pieces of segments, then we should be able to compose the predicted scene in the next frame. And we have the actual frame, JX, so we can compare them. And that completes the loop. That allows us to learn both segmentation and flow estimation at the same time. So in order to minimize the loss, we need to get the two things right. Getting segmentation right is not enough. We also need to make sure the flow estimation is also correct. Only when both are correct, we have minimal reconstruction. So we train this framework on YouTube-VOS, which has about 4,000 videos. On average, each is 5 seconds long. It covers 94 categories. These are curated by other people. If you compare to the scale of ImageNet, which has 1.3 million scenes, this only has roughly 4,000 scenes. Very small set of visual scenes we can experience. So at the output, we have a segmentation. So when we finish training, we wonder, what has the segmentation learned? We give a single image, and the rest of the 5 rows, we chose this number of segments to be 5. So you can see the first segment give you actually something related to the animal in the scene. And the rest, you have bits and pieces of the background. Because our segmentation is learned for a single image, we can apply, even though this is learned over videos, but we can apply segmentation to every frame, to every image, single image. So we see another one. You can see the same pattern appears. Object of interest, and then background broken down in different channels. Same thing to a different image. And here you see another very different scenes. Animals again, and the person dancing on the street. Now, once we get these results, we were pleasantly surprised. When we would design the model, all the channels are born equal, right? We do not say, there's one particular channel capturing this objectness. Yet somehow the objectness appeared in a particular channel. All the objectness emerges in a particular channel. Now, if you do the random initialization, this channel goes to channel 4 or 3. It may appear in different channel, but there is a concentration of objects in a particular channel. And in the paper, we have done analysis why that's the case. And we found that there's a profound reason, because the figure ground boundary, you really have to be precise. Any different estimation is causing big training errors. Without getting into specifics, what this model allows us to do is that we can automatically pick out this particular channel from the training videos we have, and then we can apply it to any new videos we have never ever seen, even though the training does not involve any labels to begin with. And on the test video, we can continue refine the model trained on this big data set, 4,000 video data set. And you can see on 3 different data sets, which all have very different characteristics, especially the last one. There's so much camera jittering, yet the bottom row show that objectness channel we use. It's fixed, and we can always look in that channel for the potential foreground. Okay, so this is our zero-shot video object segmentation results. We can also apply this to single images. And here, you can see results from, this is from a DOTS dataset, which people use to benchmark image saliency. The past work always look on different kinds of priors, like high contrast, centeredness, and all of that, or trained from label data. All these, when you look at the results, oh, this may not be too surprising because these are potentially moving objects, movable objects in the visual world. But the last column, we also show some, statue, plate, a bench, even a boulder, even some attached, something, a plaque attached to the facade of the building. We can pick them out automatically. So when we got these results, I was quite shaken. What these results tell me is that figure ground segmentation can actually learn without any preconception about low-level vision, such as edge detection, optical flow estimation, and resiliency. The only thing we have assumed is instantaneous visual constancy. We assume, given 2 frames, the world has not changed significantly, and the world is made of small number of pieces, and each piece somehow move at the same speed. That's a very, very mild, I would consider, an assumption. And this will have a very powerful application in other domains where you don't know what the physics of the flow may be different. For example, in MI, and only given these data, we will be able to do object segmentation, unsupervised video segmentation. For this kind of data, there are rapid dynamics, so there's no segmentation available. Even for humans, it's very difficult to annotate. And all the segmentation results will be very useful for many downstream tasks, such as motion correction, pathology classification, and registration. Okay, the second work I want to talk about is going a step further. I'm going to relax the constraints on the data. I only have a collection of images, not videos. Would it be possible for me to segment each object into parts? Can I recognize the objects? Some visual entities in the world can be decomposed into parts. Now, without a supervision, this seems almost impossible, right? And when segmentation is involved, there's a curious convention in the computer vision field that, we have an image, we can label them. But the thing is, the semantics intrinsically has multiple levels of granularity. So here I come up with some tree. It's one possible such organization of the scene. The top you can think of, it could denote the scene type, this outdoor street scene. The left could be foreground, the right could be background. I don't want to name them, but that's a potential organization because I think it's the grouping reflected in the labeling that matters. So then you have the red node, which corresponds to a person. And on the left, the background could have grass, paving, and rocks, okay? So you can think of, you can pre-select a vocabulary words, labels, and you can come up with such a partition. But it's rather arbitrary. And here's another possibility. For the same image, there's a dense post data set, which only focuses on the decomposition of the person. All the background is merged into one, right? So any annotation you could have is essentially an arbitrary selection of these nodes at the different levels. So why would us want to learn some model that stick to that rather arbitrary selection of semantics? So when you don't have the data, what can we learn in terms of segmentation? The approach we are taking is pixel-wise feature learning. Given an image, we want to say segment into this possible outcome, just one possible outcome, not the outcome. Okay, so that's our segmentation G. We don't know what that is. Okay, I'm going to learn a feature. It's a pixel-wise feature. So now every pixel is mapped to a point in that feature space. And I assume all the pixels in the same segment will be mapped to the same segment. So they form clusters in the feature space. So by grouping these points in the feature space, I will be able to obtain a segmentation. And by looking through a lot of images, I'm performing so-called co-segmentation. But if I do know the right segmentation, I would be able to demand the feature learning to conform to that desire that all pixels in the segmentation forming a cluster in the feature space. So that is a feature learning part. The trick is we don't know what X is. We don't know what G is. Our key insight is that while we don't know what X or G is, we assume that any good feature should support segmentations that are consistent. If you ask the segmenter, say, can you give me 3 segments? Can you give me 6 segments? The 6 and the 3 segment results should be consistent, should not be changing wildly. If we can have that consistency, the segmentation, the feature learn, and the segmentation, the outputs should probably in the right ballpark. That's the idea. So here's a schematic illustration of the implementation. We have an image. We don't know what the ground truth is. There may be some organization out there. If we can query this oracle about different granularity segmentations of different granularities, we will have different results. And we do single image augmentation. We can change, turn the thing into grayscale, flip, and change the color. And we perform multi-views co-segmentation in a batch. And let's say the same scene is partitioned into these many pieces, okay? These are fine-grained grouping. And we can continue, we can learn this clustering transformer, learn what's the next level. You know, instead of 12, what if 6? What would that feature be? We're gonna transform into new feature space and they're gonna form 6 clusters. And let's say they become something like that. We don't know what that is, but this is a coarser grained grouping. And we don't know the target, but we require the coarse grouping and the fine grouping to be consistent, okay? We also have some generic terms to quantify what makes a grouping in sort of normalized cuts fashion. Things in the same group, the feature should be compact, similar. Between different segments should be different, so on and so forth. Okay. So we benchmark our model on the unsupervised semantic segmentation. And you can see on different data sets like COCO, Cityscape, and Kitty step data sets, we achieve good results. And in particular for Cityscape and Kitty, these are the driving scenes. Most scenes are similar. So if you just focus on the image as a pattern, it's very difficult to do unsupervised learning. Once we break each scene into components, we can learn something very remarkable. And the bottom is a Cocoa Stub and Potsdam. We have much better, even higher gain, because those data sets are primarily texture segmentation. But benchmarking on unsupervised semantic segmentation is selling the method short. We can do a hierarchical semantic segmentation. Given the image, the earlier approach, there are not so many unsupervised hierarchical semantic segmentation out there. There's earlier work, OWT UCM, is based on the strength of the contours learned from some annotated data sets such as BSDS. And you can see the results when we ask for 3, 6, 12 segments. And this is on the right-hand side is ours. At the 3 segment level, we already identified these 2 sheep belong to the same category. And next we will be doing the refinement, and you can see the sheep remain in one group and the backgrounds being divided further. And we can benchmark.
Sorry to interrupt, Stella.
Yes.
I just wanted to let you know that you have like about 5 minutes left.
Okay, great.
Thank you.
Thank you. Okay, so we can do, once we know the features organized in hierarchy, we can retrieve based on feature for this area. We can pull the feature, we can do the retrieval, we can navigate in the feature space and recognizing this is part of a bigger scene, and we can always pick out the upper body, the crowd, and the lower body. So I have talked about 2 work, unsupervised mid-level. visual learning from unlabeled data and unlabeled videos and images. We're able to put a hotspot on it. We are able to learn the decomposition of either at the scene level or the object level. Now, I want to touch upon using the last 4 minutes to talk about what do I mean by mid-level. The dominant approach with deep learning for recognition is imaging. You directly identify what the category is. For that, you need a lot of data. You need to show a lot of images, repeatedly telling the model that should be done. And the work should be non-done. And supervised learning reached the superhuman performance. A lot of research have been trying to make the accuracy higher and the models leaner. But such a success, is too specialized. Different tasks need to have their own different models. What's good for one does not work for the other. And you train on one kind of data, on ImageNet t-shirt, it doesn't work in the real world, in the wild. And there's another kind. One is domain gap. The other is about this is a car parked on the side of the road you see during training, because in a normal situation you have something that when there's a flood, there's also a car on the side of the road. These are the tail end of the training instances. And so the supervised learning, the problem is a very closed world perception. That doesn't generalize. So what I propose to do is we want to do unsupervised mid-level vision. You want to focus on these composable pieces. At the low level, you only have pixels. You only have intensities. That's not much you can say about them. But with mid-level vision, there's meaningful pieces, but not yet to the full recognition, full level of recognition. And that mid-level pieces can be learned from different kinds of data. It's just like your Lego piece set. There are different vendors come up with different shapes and all that. That doesn't really matter. And that with these composable pieces, it can support a wider range of tasks. And you don't have to go all the way back to the image. So I'm focusing on this mid-level. In the Mars vision framework, you have an image. It's a bottom-up approach. Starting with the image, you first recognize this a 2D light and dark pattern. You try, what can you do? You figure out where the light-dark boundaries are, this so-called primal sketch. And then you get to mid-level. This is where you identify with a cameraman. You see what could be the foreground, what is the background, and you have this rough sense of the occlusion and what comes together as a group. And then from that, you perform recognition. You link to things you have seen in the past. You can see behind the object that's not in this image. So all this pipeline people have studied, it's universal, but the problem is very brittle. And what I have shown is that, here the mid-level is a key. If I can do 2.5D sketch well, I can do the low-level task well. I can support a variety of high-level tasks. And what I've shown today is that maybe you can go from image to the mid-level right away. And this allows you to be this buffer that sits comfortably, learning a representation that's generalizable and more robust to data variation. So I'm going to acknowledge my funding sources, and the first work is done with these co-authors. It's a NeurIPS paper last year, emergence of objectness. We are doing the appearance and motion decomposition. And the second work is our unsupervised hierarchical semantic segmentation, published this year at CVPR. And I thank you so much for your attention. I will take any questions you might have.
Thank you so much, Stella. Does anybody have any questions? I guess I'll ask a question if nobody wants to speak up. So I guess this hierarchical parts model, can you give us like a sense of how do you think this sort of like proposal that you just made about, learning generic objectness and hierarchical parts can be brought together with like the current vision and language models that we're seeing? Do you think there's a way to like co-train them, or like, use ideas from what you propose to do it in the large scale image text pre-training plus using these ideas somehow, like to combine them?
Oh, that's a great question. In fact, when I gave this talk, people who work in NLP, they really like the idea of consistency, because they can learn at the word level, they can learn at the paragraph level, but often the learned model from one paragraph to another, they are not consistent. So imposing the consistency between different granularities at the language model foreseeably can also yield much better results.
That makes a lot of sense.
Yeah.
I see. Cool. I think we're just in time. If anybody else wants to chime in with questions, feel free. Otherwise, we can wrap up here. I think we're good. Thank you so much, Stella, for giving this nice talk, and we'll reach out if we have questions that we think of later. Can I share my screen?
Yes, please. Let me stop share, or you can kick me
you.
out. Let me find my cursor.
I think you just, it'll be like a... Awesome, thanks. I just want to give the closing remarks. This was the last talk of the day. Okay, so thank you everybody for coming to this workshop. This was the end of the session and the end of the workshop. I hope you all enjoyed the great invited talks that we had today, as well as the exciting presentations from the challenge winners and the papers that were presented at this workshop. We hope that this new direction of like computer vision in the wild and this workshop will inspire more work on this area of open world recognition, and hope that it will help our community to work together to apply all of the impressive results that we're seeing now from large image and text models that and the results that we currently measure on standard benchmarks, and extend them to solving real world problems in the wild. We hope to see you all in the future iterations of the workshop, and I wish you a wonderful rest of your conference week. Thank you.